when we say operational amplifier, you will see this symbol. And op-amp is represented as a triangular shape device with two inputs and one output. So in terms of its functionality, the op-amp change voltage amplitude and also the polarity of the voltage. So the characteristics of op-amp, it has high gain, high impedance, infinity, and low output impedance. So the ability of the op-amp to amplify signals with very high impedance at the input side, but low impedance at the output side. So an op-amp can be used to make many circuits such as the oscillator, the filter, regulator, comparator, and many more. Into differentiator, integrator, so many others. The list can goes on. So today we just learn about the basics of op-amps. There are many kinds of op-amps produced, and op-amp is actually small circuits comprised. The op-amp itself is integrated circuit. The inside of the op-amp, it contains many transistor circuits. So the op-amp can be made of BJT circuit or FET circuit, depending on the op-amp. So we have like 741, LM322, LM, so many varieties of op-amp. But the commonly used an op-amp is 741 op-amp. So in this diagram, it shows the internal circuitry of an op-amp. For example, in this circuit, you have how many transistor in this circuit? Q1, Q2, Q3, Q4, and then Q5 here, 6, 7, all together 17 here. 17 transistors inside an op-amp. A compact circuitry inside an op-amp. An op-amp can be 7 legs or 4 legs. This is the schematic diagram of a 741 op-amp. So a 741 op-amp internally has many BJT circuits. Okay, but the connection of the op-amp, you will only see a few legs of the op-amp that you are going to connect to make the op-amp functional. Okay, so despite of having so many transistors inside the op-amp, we can always simplify the application of the op-amp itself. So the symbol, as I mentioned just now, symbol for an op-amp is always a triangular with two inputs. One input is labeled as negative, another input is labeled as positive. So the negative input is called the inverter input. The input with label as plus sign is the non-inverting input. And the output is only one output. And to make this op-amp working, we need to apply bias voltage. And the bias voltage normally, two bias voltage, negative V and plus V. So depending on the voltage, based on the circuit diagram, circuit specific device sheet, you will have information regarding the safe working supply voltage. So here would be VCC for the BJT lah, inside the circuit. So normally for 741, maximum would be 15 volt. If I'm not from the data sheet, I think it will say negative 22 to negative plus 22, but normally we use 15 volt. Okay, as long as you do not use, you do not apply the voltage, biasing voltage higher than the safe voltage supply, the op-amp will be working normally in good condition. But if you apply slightly below, your op-amp can last long. But you cannot apply the VCC too low. It has to be in the range of the working range. So this is the symbol. In the right side of the figure, you will have the schematic, not schematic, the actual representation where a 741 op-amp is actually a 4-leg compact IC, and the 4 legs in the left side you have legs level 1, 2, 3, 4, and the right leg level 5 from bottom, 6, 7, 8 upwards. So for each of the leg, it represents the specific connection. For example, leg number 1 is for offset null, the inverting and the non-inverting inputs are for the leg 2 and 3. Leg number 4 is negative V bias voltage, and 7, leg number 7 is for the positive bias voltage. The output is measured at leg number 6, and leg number 5 and 1 are actually offset null. And leg number 8 and C means not connected. So leg number 8 is just open. It is there to make the circuit stable, so that you have 4 in the left side, 4 in the right side. So when you attach the op-amp, it is stable. So kalau kaki 7 ni ada satu tergantung, maybe it not stable because of one leg is missing. So leg number 8 is just not connected, but it's there. So this is the op-amp appearance. One is symbol, one is actual schematic lah, outer surface schematic. Okay, for an op-amp, we will have, let's consider the single-ended input. Okay, an op-amp can amplify an input with the same polarity as the input signal. When you apply the non-inverting, when you apply the inverting input to the ground. So for example, when you apply the input to the non-inverting terminal, input terminal, the output will be same polarity. Same polarity means same phase. So if you when you give a positive phase of the input, the output will have a positive phase also, with amplitude that is depending on the gain of the amplifier. Okay, and if you apply Vin at the inverting input terminal, the negative terminal, the output voltage will become out of phase by 180 degrees. So the amplified output with the opposite polarity as the input signal. So here you see when you apply your sine wave, positive first, negative, but the output will appear negative first, then positive phase. So this is, say, 180 degrees out of phase. Okay, so that is the difference between applying input to the inverting, non-inverting input will produce same polarity. But if you apply input to the inverting input terminal, your output will be out of phase. Okay, this is the basic theory. However, in reality, you will have to consider few normal conditions for op-amp. So let's consider, let's calculate the gain for the amplifier. A basic gain equation is always V out over V in. This is the common, the standard equation for gain. So if we have this op-amp not connected without any feedback loop to the input side, we will have an open loop gain AO multiplied by the input. The input of the op-amp will always be two inputs from negative terminal to the positive terminal, or from the non-inverting to the inverting terminal. Okay, so when you have input V in to the plus terminal, this would be 0. So the input is only coming from V in, because V negative here is 0, V plus with some values. So because this is 0, the difference between V plus and V minus is due to the value of V in only. So therefore, V out is actually the gain, open loop gain, AO, multiplied by V plus only, or V in, where V plus is having the value of V in. Okay. This is the condition when your inverting input terminal is grounded. Therefore, you will produce a gain equals to V out over V in, which is called A open loop gain. Okay, if you apply, you change the polarity, not polarity, you change the input. Now you apply input at the inverting input terminal, which is the V minus, and you ground the the input terminal, the inverting input terminal. So you have V plus is 0. Okay, so your V out now is equal to AO times the difference between V plus minus V minus V minus. So you will get a value of negative AO times V in. Now you see you have a negative sign in front of the equation. So then you will have your gain is equals to negative AO, because gain, although it's the value of VO over V in, now it becomes negative AO. So this is why we say negative means opposite. So this is only happen when you have your V plus connected to the ground. Okay, and you have you say when you apply V in to the inverting input terminal, you will produce a negative value. So from that, we mention this is the inverting input with a minus sign. For a amplifier, in reality, there should be some values between V negative and V positive here. So actually, the amplifier is amplifying the amount of voltage difference between the two input terminals. Okay, and if you apply V in here, so you would expect same voltage enter through the V minus and through the V plus. Okay, we have same input signals at both inputs. both of the input terminals are equally amplified but in opposite polarity. These signals cancel out, making the output become zero. However, there will be very small output produced even though you have a common connection between the inverting and the non-inverting inputs of the op-amps. Okay, and it will produce differential and the common mode operation, whereby for an op-amp with arbitrary input voltage V1 and V2, there will be differential input signal Vd, and normally the value of V1 and V2 will be very small, few millivolt, but at the output you will have very small volt. Okay, and the V1, the difference between V1 and V2 at the input terminals will give differential input voltage, and the common input signal Vc is actually the average of the two input voltages at the input terminal. So Vc is the common mode is equals to average, which V1 plus V2 divided by 2. But at the output of the op-amp, VO is going to be the voltage due to the differential input and also the voltage due to the common mode signal. So therefore you will have VO is the gain, differential gain times the VD plus the gain due to the common mode arrangement multiplied with the common mode voltage. Okay, and you will also have common mode rejection ratio for an op-amp, where common mode rejection ratio is actually the magnitude of the differential gain, or the ratio of differential gain to the common mode gain. So you will have AD divided with AC. That would be the common mode rejection ratio. And CMRR normally we refer as dB unit. So if you want to make it into dB, you have to 20 log dB lah. Okay, and the gain, the CMRR simply ratio of AD to AC. Okay, the output voltage of the op-amp VO is equals to the differential gain plus the common gain, the voltage due to the differential gain and the voltage due to the common mode. If you rearrange this equation, you will produce, it is going to be equals to AD times VD multiplied by 1 plus 1 over the common mode rejection ratio multiplied with VC over VD. So if you are given data sheet and stated the common mode rejection ratio value, you can calculate your VO if you have your differential gain, and you can test the performance of the op-amp. Okay, so basically, because CMRR is in the bottom of the equation, when CMRR is large, the output voltage will be influenced mostly by the differential signal. Okay, because of this VD, differential signal is the VD, while the effect of the common mode component is greatly reduced. Okay. The common mode rejection ratio, an op-amp has input voltage of VI equals to 150 microvolts and VI2 equals to 140 micro, between 120 to 140 and 150. The differential gain for this situation will be the difference between 150 minus 140 microvolts lah. So therefore, you will get about the differential gain. No, this is the gain. The gain is around 4,000. So the differential voltage will be 10 microvolts. So compare the output voltage with the component of differential input signals when the CMRR of the op-amp is 1,000 and 10,000. You can compare this one at 100 CMRR and at 10 to the power of 5 CMRR, it will be very large difference. And the CMRR indicates the op-amp's ability to reject a signal applied simultaneously to both inputs. The higher the CMRR, the better the op-amp. Typically, an op-amp with CMRR in the range between 80 to 120 dB is a good op-amp. CMRR, however, decrease when frequency increase because of the CMR is in the bottom of the equation. So it is actually inverting, or we can say inversely related to frequency. Okay, for an op-amp, because an op-amp consists of many transistors inside it, we can always evaluate an op-amp circuit by evaluating the AC equivalent of the transistors. So we can simply, despite of the many transistors inside the op-amp, we can always represent it as one circuit. Okay, and for example here, you will have you can convert differential gain at the input VD. So you will expect there will be V1, V2 at the input terminal, and Ri will be the internal resistance of the op-amp. And at the output side, you will have the differential gain AD times VD, and you have RO, and you measure the output voltage VO across this. So from this figure, practically, you have this arrangement of input and output of the circuit. But the ideal situation is actually you will have V differential here. The resistance at the input side will be very large because an op-amp characteristic has infinity impedance. So therefore, it is like an open circuit, and because of high input impedance. And at the output side, the RO is very small. So as if there is no resistance. So therefore, it makes your op-amp in the ideal situation is only represented as VD at the input and VO measured across this AD times VD. Okay, so the input signal applied between the input terminal sees the impedance Ri, typically very large, infinity value, and the output voltage is shown to be the amplifier gain times the input signal taken through the output impedance RO, typically very low, or we can assume like 0. And the ideal op-amp circuit would have infinite input impedance, 0 output impedance, and infinity voltage gain, very large gain. However, in practice, we cannot have infinity gain because of the bias voltage of the op-amp. You cannot produce amplification higher than the supplied voltage. So if you have your op-amp supplied with VCC negative 15 to 15 volts, definitely the output of the voltage of the op-amp cannot be more than 15 volts because it saturates at supply voltage. the bias voltage. Okay. The op-amp gain, we can have two kinds of gain depending on the operating of the op-amp. We can have an open loop gain or we can have the closed loop gain. The open loop gain is the configuration where there is no feedback from the output to the input. In the open loop configuration, the gain can exceed to 10,000. But for the closed loop, the configuration reduce the gain very much because there will be feedback by connecting resistors to the input. In order to control the gain of an op-amp, it must have the feedback. And this feedback is a negative feedback. And the negative feedback reduces the gain and improves many characteristics of the op-amp. For the open loop, it can make the op-amp become unstable. So to avoid instability of the op-amp, we always use a closed loop connection for an op-amp. How to use the op-amp? We would like our op-amp to amplify the input signal by a factor of an arbitrary value. However, the open loop gain is fixed and it will be too large. We need to make the amplification system as the closed loop using some external circuit. And there are two configurations of using the external circuit. Whether we set the op-amp working in the non-inverting arrangement or in the inverting arrangement. Okay. If we consider the closed loop configuration, we will apply V input if we connect to the inverting input and we connect external resistor RF. We call it RF because this resistor is actually the feedback resistor from the output terminal feedback to the input terminal. So in this case, because the inverting input terminal is grounded, so V1 here, so V2 will be here, and this V2 is actually 0. So now you only see current pass through R1, RF, and you measure at VO. Okay, so for this closed loop configuration, we can sketch the AC equivalent circuit. We will have R1, Ri, and the RO in series with the AOL gain or open loop gain multiplied by the V in. Okay, and the RF is actually the resistor that is connected from the output to the input. So this will be the AC equivalent circuit for this simple closed loop arrangement. So the open loop gain AOL, Ri is input impedance, Ro is the output impedance, VO is measured as the value the multiplication of A open loop times V in. Okay, and V in comes from the input terminal, the inverting input terminal. Since A open loop is large, we consider infinity gain. Vi is equals to Vo over the open loop gain. That would be, because this is a large value, so it will make Vi is almost zero value. But the principle of ideal situation of an op-amp, Vi is actually the difference between the inverting and the non-inverting input terminals. So Vi is actually V plus minus V minus. Because V plus is grounded, therefore V plus is equals to V minus and equals to 0. So it means that V minus is also grounded. Okay, this concept is called the virtual ground. So because you connect this VI to the ground, so you will have a virtual ground to the other input terminal as well. So using KCL, so now nothing flow in the bottom, only current flow in the top path. Okay, so therefore, if you consider voltage drop across here, voltage drop across here, and voltage output. So V1 minus VI divided with the R1, this is Kirchhoff's law, minus VI divided with Ri is equals to VI minus VO divided with the RF. Okay, because VI is 0, therefore your V1 over R1 is then becomes value of negative VO over RF, and VO over V1, which is the gain now, because you want to consider output over the input, is actually a factor of RF over R1. Okay, so there is no need for you to know the actual value of Ri. So the voltage gain now is simply equals to RF over R1 with a negative sign, because you apply V1, V in you, at the inverting input terminal. So you have the gain is a negative gain. Okay, and the circuit provides a voltage gain with a 180 degrees phase inversion from the input signals. Okay, you can use to solve for this one, you can use the superposition theorem. Apply your circuit theory 2 to solve for the equation. But basically, when you connect your op-amp with the arrangement that the input is applied to the negative input terminal, you will have inverting amplifier, where the inverting amplifier gain is always AV is equals to negative RF divided with R1. So in other words, you can estimate the gain of the op-amp by only using the external resistor divided with the resistor that is connected to the input terminal. Okay, the golden rules for op-amp is always two basic rules. Number one, there will be no difference. So in other words, voltage difference between the input terminals must be 0. When you have V1, V2, the difference will be 0. Okay, the input draws no current. So meaning that there is no current flow into the inverting input terminal and to the non-inverting input terminal. Okay, and with that arrangement, you can make the op-amp into inverting amplifier or non-inverting amplifier, summing amplifier, unity follower, integrator, differentiator, comparator pun boleh, and so ada many other arrangement. Okay. Before we go with the specific arrangement, I stop here. I want to show some videos on basics of the op-amp. Let me show you some videos. Okay, let us see some videos. I haven't have time to. Can you listen the sound? Dengar suara tak? Suara daripada video tu?
Dengar.
Dengar.
Okay, good. So I'll play.
Hey friends, welcome to the YouTube channel all about electronics. So in this video, we are going to talk about the basics of the operational amplifier. And in the upcoming videos, we will talk more about this operational amplifier and we will see how we can design the different circuits using this operational amplifier. So as its name suggests, this op-amp is basically a amplifier and the basic job of any amplifier is to amplify the input signal. Now let us understand why it is known as the operational amplifier. So in early days when digital computers were not evolved, at that time the different mathematical functions like addition, subtraction, integration and differentiation were performed using this operational amplifier. So just by connecting a few resistors and capacitor, it is possible to perform different mathematical operations. And that is why this amplifier is known as the operational amplifier. So now if you see the circuit symbol of operational amplifier, it can be represented by this symbol. So it consists of two inputs and one output. And most of the amplifiers consist of a two power supply, the positive and the negative power supply. But there are many op-amp ICs which runs on the single power supply. So now in this operational amplifier, the input terminal which is marked by this positive sign is known as the non-inverting input terminal, and the another input terminal which is marked by this negative sign is known as the inverting input terminal. And it will be get clear to you very shortly why it is known as the non-inverting as well as the inverting input terminals. So now if you see this operational amplifier, it is a one kind of differential amplifier with a single output. It means that this amplifier amplifies the difference between the two input signals. So let's say V1 and V2 are the input signals which is being applied to this operational amplifier, and let's say the gain of this operational amplifier is A, then the output will be equal to A times the V1 minus V2. So let's say if we have applied the single input to this operation amplifier and we have grounded the another input terminal, then at the output you will get a times V1, where A is the open loop gain of this operational amplifier. The reason it is being known as the open loop gain because it is the gain of the operational amplifier when there is a no feedback from the output to the input side. So suppose if you are applying the sinusoidal signal over here, then at the output that sinusoidal signal should be get multiplied by the factor of this gain, and at the output you should get a amplified sinusoidal signal. Now here the phase of this output voltage will be the same as the input voltage. Likewise, whenever we are applying a input to this negative terminal and we are grounding the another terminal, then the output of this amplifier will be equal to minus A times the V2, because the difference between these two input terminal will be equal to 0 minus V2, that is equal to minus V2. So suppose let's say if we are applying the sinusoidal signal at the input, then at the output we will get the amplified sinusoidal signal which is having a 180-degree phase with respect to input signal. That means the output will be get inverted by a 180-degree, and that is why this input terminal is known as the inverting terminal, because the output will be get inverted with respect to input. So now here suppose if we apply the input signal between these two positive and the negative terminals, then at the output we will get a times this differential input signal, where here this A represents the open loop gain of this operational amplifier. Now this operational amplifier is very high gain amplifier, and the value of gain used to be in the range of 10 to the power 5 to the 10 to the power 6. So let's say even if we apply the 1 millivolt of signal between these two terminals, and let's say if the gain of this op-amp is 10 to the power 5, then at the output theoretically we should get 1 millivolt signal that is multiplied by the 10 to the power 5, that is equal to 100 volt. Or let's say if we apply 1 volt of signal, then theoretically we should get a output as a 10 to the power 5 volt, but that is not possible, and the output of this op-amp is restricted by the biasing voltages that is being applied to this op-amp. So the output voltage will be between this biasing voltages. So if you see the voltage transfer curve of op-amp, then it will look like this. So here the x-axis represents the differential input that is being applied to this operation amplifier, and the y-axis represents the output voltage of the amplifier. And here the slope basically represents the gain of the amplifier, which used to be in the range of 10 to the power 5 to the 10 to the power 6. Now here let's say the gain of the op-amp is 10 to the power 6, and let's say we are applying a 1 microvolt of signal. Then at the output we should get a 1 volt of signal. Likewise, let's say if we apply 10 microvolt of signal, then at the output we will get a 10 volt of output. But as we increase this input signal, then you will find that after some value of input signal, the output will be get saturated to the value plus Vset, which used to be less than the positive biasing supply. So in this way, as soon as the input voltage goes beyond some certain value, the output will be get saturated to the plus saturation voltage. And same is true for the negative input voltages. So as soon as the input voltage goes beyond some threshold value, at the output you will get a minus saturation voltage. So whenever this operational amplifier is used in an open loop configuration, that means there is a no feedback from output to the input side at that time. Even if we apply a small input signal between these two input terminals, then also you will find that the output will be get saturated towards the positive or the negative biasing voltages. So this particular characteristic of the op-amp is particularly useful when we use this op-amp as a comparator. So this is one of the application in which this op-amp can be used. But if you see this op-amp can be also be used in so many other applications, like in designing the active filters, oscillators, waveform converters, and analog to digital and digital to analog converters. And if we count the list will go on. So basically this op-amp is very versatile IC, and you will find this op-amp in so many applications. Now the reason this op-amp is used in so many applications is because of its different characteristic. So let us see the different characteristic of the op-amp because of which it is being so versatile and used in different applications. So before we see that, let us see the equivalent circuit of the op-amp. So as you can see here, this Ri is the input impedance of this op-amp. Likewise, this Ro represents the output impedance of this op-amp, and the output voltage of the op-amp will be the open loop gain multiplied by the difference between the input signals V1 and V2. So now before we see the different characteristic of the op-amp, let us see the different characteristic of the ideal op-amp. So the ideal op-amp should have this input impedance Ri that is equal to infinity, so that whatever input that is being applied between the input terminals will directly get applied to the op-amp. Similarly, the output impedance of this op-amp should be equal to 0. That means whenever we are applying the output load to this op-amp, then the output voltage should directly come across this output load. Then if you see the bandwidth of the ideal op-amp, the bandwidth of the ideal op-amp should also be equal to infinity. It means it should support all the frequencies starting from the 0 Hz up to the infinite. Similarly, the gain of the ideal op-amp should also be equal to infinite. Apart from that, whenever these two input terminals are 0, that means the input to this op-amp is 0. At that time, the output of this ideal op-amp should be equal to 0. Now, apart from these characteristics, there are few more characteristics of the ideal op-amp, that is slew rate and the common mode rejection ratio. So we will see more about these different characteristic in detail in separate videos, but let us see the basics of this different characteristic. So in a simple way, if I say the slew rate is basically how fast the op-amp is able to reach its final value, and that is particularly useful when we are applying a square wave to the op-amp. So let's say we have applied this square wave to the input of this op-amp, and at the output we are getting this output waveform that is varying from 0 volt to the V saturation. So the ideal op-amp should be able to reach from the 0 volt to the Vset volt in a 0 time. So for the ideal op-amp, the slew rate should be equal to infinity. Generally, the slew rate is defined in a unit of volt per microsecond. That means how fast the op-amp is able to respond to the output voltage. Then there is another parameter which is known as the common mode rejection ratio. So let us understand very briefly what do we mean by this common mode rejection ratio. We will talk more about it in a separate video. So let's say if we are applying the same input voltage to this V1 and V2, then the difference between these two voltage will be equal to 0, and at the output we should get a 0 volt. Likewise, when we are applying a different input voltages V1 and V2 to this op-amp, then at the output, the difference between these two voltages will be get amplified by certain amplifier gain. So this common mode rejection ratio basically defines how well the op-amp is able to reject the common input voltages that is being applied to both its input terminals, and how well it is able to amplify the difference between the two voltages, and it is generally defined as the ratio of differential gain divided by the common mode gain. So for the ideal op-amp, the value of this common mode rejection ratio should be equal to infinity. So here is the list of different ideal op-amp characteristic. So the ideal op-amp has an infinite input impedance, infinite open loop gain, and infinite bandwidth and slew rate. And in this ideal op-amp, whenever the input is equal to 0, then at that time the output is also 0. And this ideal op-amp has a infinite common mode rejection ratio. But if you see any practical op-amps, they used to have finite input as well as the output impedance. Generally, this input impedance is in the range of mega ohms, while the output impedance is in the range of few ohms. Similarly, the open loop gain of the op-amp is not infinity, but it used to be in the range of 10 to the power 5 to the 10 to the power 6. Likewise, for the practical op-amps, whenever the input is equal to 0, at that time also you will get some output at the op-amp. Generally used to be in the range of few millivolts. That is known as the offset voltage, and we will talk more about it in the separate video. So here is the list of different parameters and the values of different parameters for the general purpose 741 op-amp IC. So now if you see the different op-amp ICs, they are optimized for the different parameters. So let's say if one op-amp is optimized for the very high slew rate, while the another op-amp is optimized for the very high open loop gain. And if you see some other IC, you might find that it is optimized for the very low offset voltages. So depending upon your application, you need to decide which parameter is critical for your application, and based on that you can decide which op-amp is suitable for your particular application. Now so far we have seen this op-amp in an open loop configuration. That means there was no feedback from output to the input. Now in the next video we will see what happens when we provide the feedback from output to the input side. So I hope in this video you understood the different characteristics of this op-amp. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.
Okay, so that's I think it summarize what I have explained in a more nice figure, I think. Okay, now let's see another video which I found and very interesting.
If you ever used ICs in your projects,
This is
then
the
you
is
might have noticed that most of them contain a triangle shaped component in their simplified schematic. Those triangles are called operational amplifiers, also known as op-amps. And since they are very common and useful for analog and digital electronics, I have used them before in a couple of different projects. So in this video, I will show you what op-amps are capable of doing and how to handle them properly. Let's get started. First off, you can get op-amp ICs in a dual inline package with either 14 pins that usually features 4 op-amps inside, or 8 pins that features 2 or only 1 op-amp inside. As an example, I will use the popular LM358 dual op-amp whose ground pin I connected to 0 volts and V plus pin to 12 volts, which is fine because it does not exceed the single supply range of the IC. Next, I apply the voltage of plus 1 volts to the plus inputs, aka the non-inverting input of the op-amp, as well as a 10 kilo ohm pull-down resistor to set the reference voltage to ground. Then I created a voltage divider consisting of a 5.1 kilo ohm and a 1 kilo ohm resistor in this constellation between the output pin and the negative inputs, aka the inverting inputs. As a result, I received a voltage of 6.1 volts at the output, which equals an amplification factor of 6.1. But why? Well, the first golden rule of op-amps gives us the answer. The output of an op-amp will always attempt everything to keep the voltage difference between the inputs at 0 volts. That means there needs to be the same voltage drop across R1 as the input voltage Vin. If we now add the voltage divider formula to this and the fact that the gain is the output voltage divided by the input voltage, we finally get the classical formula for the gain of a non-inverting op-amp. Such a circuit can be used to amplify the signal from a sensor, like for example a PT100 temperature sensor, or the AC signal from an electret microphone. This one creates maximum voltage peaks of around 100 millivolts AC, which I can now easily amplify with a gain of 48 by changing the 5.1 kilo ohm resistor to 47 kilo ohm. But when we observe the outputs, we notice another problem. Only the positive AC voltage got amplified, because the output voltage swing is limited to the supply voltage. That means we would need positive and negative 12 volts to successfully amplify the complete AC signal, which I can demonstrate with my lab bench power supply. But since that is normally not an option, we could also add a DC offset to the plus inputs. This way the complete amplification does work to some extent, but because we are amplifying a DC voltage as well this time, we hit the 10.8 volt output limit of the op-amp pretty quickly. Why 10.8 volts instead of the 12 volts of the supply voltage? Well, there is no perfect op-amp. The ideal one would also have an infinite high input impedance and thus no input current could flow, which is not true. It would have an output impedance of 0, which means we could draw as much current as we want, which is not true, and the list goes on and on. But on the other hand, there does exist rail-to-rail op-amps that can achieve an output voltage which equals their supply voltage. And as long as you don't want to create precision circuits, such non-ideal parameters do not matter that much. But let's get back to the microphone amplifier. A more suitable circuit for this task would be an inverting op-amp. In this constellation, the plus input is connected to ground, which means the minus input must have a voltage potential of 0 volts as well. And since the second golden rule of op-amps says that the input draws no current, the current through R1 must be the same as through R2. This results in the classical formula for the inverting op-amp circuits. And by connecting the plus input to a DC offset voltage instead of ground, we can amplify the microphone AC signal completely without amplifying any DC voltage. The output signal can then be connected to a speaker, but just like I said before, because of the small maximum output current, the sound is almost unhearable. The last important rule when working with op-amps is that when no feedback is attached between the outputs and inputs, the output will either jump up to the maximum output voltage when the plus input has a higher voltage than the minus inputs, or in reverse, the output will jump down to the minimum output voltage when the minus input has a higher voltage than the plus inputs. The reason is the high open loop gain of the op-amp, and such a configuration is called a comparator. And there also exist separate comparator ICs that achieve a faster response time than the average op-amp. And with those three golden rules in mind, you can understand and build constant current sources and loads, voltage followers, integrators, differentiators, inverting, non-inverting, difference and summing amplifiers, Schmitt triggers, and the list goes on and on. As you can see, it is a versatile component and there's much more to say about it than what I just presented. But that is a subject for another video. Until then, don't forget to like, share and subscribe. Consider supporting me through Patreon to keep such videos coming. Stay creative and I will see you next time.
Okay, I think those two videos are very interesting. It shows theory and then how actually you can evaluate, you can see the performance of the op-amp. Okay,